Welcome to our video on TensorFlow Eager, where we're going to go over how to use the new TensorFlow Eager execution mode. To get our minds in the right place, we'll begin by going over the main differences between the traditional TensorFlow approach and TensorFlow Eager approach. Then we'll re-implement the code from video 1.5 using the TensorFlow Eager approach. By now, we're all very familiar with the traditional TensorFlow programming approach. We define a bunch of operations, and that defines our computation graph. Then, to actually run our computations, a session is created either by us or some TensorFlow estimator object, and one or more session run calls are made to perform those computations. This is also made clear when we try to print our variables, and we just get generic outputs as shown on the slide. This is one of the reasons that TensorFlow has a higher learning curve than other frameworks, since most people are used to things like NumPy. In NumPy, operations are executed as soon as you type them out. Spoiler alert, that's what TensorFlow Eager is going to do for us. Now we see what the print outputs look like when we're in TensorFlow Eager mode. It actually shows the data. We actually see the numbers and the result of the computations like we would expect if we were coming into TensorFlow with no prior understanding of the static computation graph paradigm. And that's because with Eager execution enabled, TensorFlow basically acts like NumPy and executes the operations immediately. This makes it a lot easier to get started with TensorFlow and to write TensorFlow programs in less time. So you may be wondering, is this a TensorFlow revolution? Are static computation graphs dead? Well, not quite. As of March 25th, 2018, the date of this recording, it's still recommended to go with the traditional approach if you're concerned with speed, efficiency, or running in a production environment. The good news, though, is that TensorFlow team is working quite hard to make it trivial to convert your code from one approach to the other. Before we dive into coding, this might be a good time to pause the video and review what we did in video 1.5, where we wrote some TensorFlow code for training a simple neural network on random data. We've come a long way since then. To show how to work in Eager execution mode, we're going to re-implement the code from video 1.5 to use TensorFlow Eager. Let's get started. Okay, so beginning at the very top of the file, I just want to show that we have a little bit new imports. So as usual, import TensorFlow as TF. And for now, we have to import from contrib the Eager module as TFE, as is typically done in the tutorials and documentation. I'm assuming that in some future version of TensorFlow, this import will not be necessary, but as of version 1.7, which is what I'm currently running, this is how you get the TensorFlow Eager module. It's giving the argparse stuff as usual. And so this is the main line where we actually enter TensorFlow Eager mode. So you have to just type tf.enable eager execution. If you're running either 1.5 or 1.6 version of TensorFlow, then you have to do TFE. So it recently just moved out of the contrib module, the enable eager execution function. But either way, depending on what version you're using, this is what you call, and from here on out, we are in TensorFlow Eager mode, and we cannot leave TensorFlow Eager mode in this Python session. We'd have to restart the Python interpreter and remove this line if we wanted to get back into normal TensorFlow mode. Scrolling down to our main function. Okay, hopefully you reviewed the video from 1.5. These are the same things. We're just putting them in an hparams object because that's a little bit cleaner. Num classes, num features, num epochs, just the standard stuff to set up our basic neural network. Still using the same numpy.random methods to get the random data for generating to put in our neural network and see if we can fit the random data. A little bit different now as I'm using the tf.data module, which was still in contrib when we actually made video 1.5. TensorFlow has come a long way since then, as well have we. But hopefully by now, you're familiar with what this is doing. So we say tf.data dataset from tensor slices. We put our stuff that we're going to feed into the network here and our labels here. So this was before in the video 1.5, this was the fake inputs, I believe, variable, and this was fake labels. We batch it up into hparams.batchSize, so now we have a TensorFlow dataset that we can feed with both random inputs and random labels that we can feed to our neural network and train on. Same loop as in video 1.5, except for this is the main introduction. We have our code in a class now instead of just defining the operations in sequence. And there's actually a reason for that. In TensorFlow Eager, it is recommended to put your code in a class, and so we'll scroll up and see why. So again, we're defining our model as simple neural network, but passing the hyperparams to it. So let's scroll up and see the implementation for simple neural network. Expanding here. So first and foremost, I am subclassing tfe.network. So tfe.network gives us a number of interesting utilities. In general, it's going to make our simple neural network class function just like a TensorFlow layer, so that we can actually compose larger and larger models with components of simple neural networks. So we could make, say, a complex network class that contains two simple neural networks applied on top of each other. Things like that. It kind of puts our model code into the TensorFlow framework paradigm. So what we do when we initialize or construct our object, our simple neural network object, if we're using TensorFlow Eager, we define the layers just like we did in the video 1.5 video, but all of those are wrapped in self.trackLayer. So self.trackLayer is a method that we get when we subclass tfe.network, and it just basically does what the name says it does. It allows the TF network class to know exactly what the variables are, the TensorFlow variables, and different layer objects that we're going to use in our model. And so that's what it grabs when it tries to implement things like the variables property and wrap our class as a layer in general. But so here we see actually the same code from video 1.5. It's a sequence dense layers. I'm using the uppercase dense instead of lowercase dense, which is not super important. Using a class instead of a function allows us to reuse that operation a little bit easier. So we define our set of hidden layers just equal to the number of num layers. That's how many hidden layers we have, and they're going to be applied one after the other. Our output layer, just as in the video 1.5, is just another dense layer. This is just a very simple multi-layer perceptron neural network sequence of dense layers with the ReLU activation function followed by a logits layer. We also define our optimizer. In the video 1.5, we use the tf.contrib.layers.optimize loss function, as we've used many times throughout the course. Here we're going to do things a little bit more explicitly so you can see what's going on and just use the atom optimizer directly. And now we're going to see in the next line something that is unique to TensorFlow Eager, tfe.implicit gradients. So at tfe.implicit gradients is going to allow us to get a list of all the gradients of every variable that's involved in the function that we pass to it. So before we get to that, let's see what this is. We're passing self.loss function. So let's go first. We're going to take a quick step into the self.loss function so we can see what we're passing to it, and then we'll return to here and go a little bit more detail into what this gives us. So here is our self-loss function. It accepts two arguments, x and y, which unsurprisingly are going to be a batch of the fake inputs data and a batch of the fake labels data. And I call logits equals self of x. So this is, you can see why our class is behaving a little bit like a TensorFlow layer. So it's under the hood calling self.call. We implement that ourselves. This is just another part of the procedure when implementing a class that inherits from tfe.network. So our call is going to accept input, which is just going to be the batch of fake inputs. We set x equal to input because we're about to iterate, so we're just doing sequentially x equals layer of x, piling on those hidden layers one after the other. Return self.output layer of x, so this is a really simple function. We're just literally applying each layer one after the other, and then returning the final output, which is the logits. Define our imp top k, which is going to count the number of predictions we got correct out of the batch, exactly the same as video 1.5, getting the number of correct and converting the fake labels into one-hot encoded labels. This returns the result of TensorFlow losses softmax cross entropy on those labels as against the logits. And since we're in eager execution mode, this is literally going to return the loss value, not just a TensorFlow variable that will eventually hold the value of it once we pass it through some session run call. Everything that we're typing here is actually being executed as soon as it's run or called through a function. Okay, so we've seen what our loss function is implemented like. So again, we have our grads function here. Something that you're going to see a lot when you look through the TensorFlow Eager tutorials is the process of defining your grads function and what you pass to it. We pass our loss function because our gradient descent updates are going to be the gradients of the loss function with respect to the inputs, collecting all the intermediate gradients along the way. That's why we use implicit gradients, because that's going to give us the gradients of the loss function with respect to every variable that occurs within inside of that loss function, and as well as our computation of our logits. Okay, and notice how we haven't actually called any of these variables yet. Nothing has actually been created. This has all just been set up. We've just defined our dense layers. The variables for these dense layers are not really created until you call their .call method. Again, we didn't call the loss function. We just said this is what you should call when you want to take the gradients. So this is all just set up. Almost actually a pretty similar feeling to how we had when we did the traditional TensorFlow approach. All the magic is going to happen when we start entering our training loop. So let's scroll back down to main. All we've done so far is just see how to create our simple neural network. So let's see what training looks like. Again, this loop is exactly taken from the 1.5 video. We loop over some number of epochs that we have specified beforehand. And now the training loop, all it does is it calls on our model the run train epoch method, and it passes in the data set that we just created. So all the magic is happening here. So let's see how this is implemented. Run train epoch. and that's actually just this very small method here. The reason why I wrapped our fake labels and fake inputs into a TensorFlow dataset is going to be clear in this function, because it's nice and clean. I pass in a dataset, and I can just call for_xy in tfe.iterator. So TensorFlow eager has its own iterator object. It accepts a dataset, and it yields, for us, it's going to be yielding a x, which is a fake inputs batch, and y, which is the corresponding fake labels batch. So if we have that, we just run a single train step on x and y. And look how small this one is too. All these nice small methods, very, very clean. Run train step on x and y. We call our optimizer, the one we created in our constructor. And we just call apply gradients on our grads function, which we also just went over in our constructor. We pass in x and y. And I put those in tf.constants so that they're already converted to TensorFlow variables. As of the version 1.7, keeping them inside NumPy variables gives it an error. Wrapping it in the dataset actually fixes this problem, but I have this code here just in case you wanted to reuse it without a dataset. And that's it. Notice how we didn't have to have any mention of a session. We didn't have to rely on an estimator for handling the session for us, so it's definitely got its appeal. Again, it's not going to be quite as fast and optimally efficient as using the traditional approach if you're using these large models in a production environment, but it is very quick to set up a basic set of code, and it feels more like PyTorch, which is one of the motivations TensorFlow had for making TensorFlow eager. And so real quick, let's just see what some output of this looks like. So here I'm just going to execute it. See the snippet we had from the slide earlier showing on the screen. And at the bottom we see the training progressing. TensorFlow eager, it just works. Much less setup required. That's it for our brief introduction to TensorFlow eager. I encourage you to click through the additional links in the resources slide. As always, make sure to read through the links here for an in-depth look at the topics covered today. Just one more video left for us. In the next and final video, we're going to review what we've learned throughout our course and discuss possible next steps in the TensorFlow journey.